everyone awake for this really, really important session. It deals with a very urgent challenge that it's delightful to see how the HDI community is looking into. It's about collaborating with AI. This morning we have 7 papers to be presented, and we have including also 2 honorable mentions. So be ready for a nice tour. First, I'd like to introduce, we have a little bit of shift in the order of the presentations. So I'd like to introduce Zhao who will present the first paper called Spark Tales, Facilitating Cross-Language Collaborative Storytelling Through Coordinator AI Collaboration.
Wait. Hello, I'm Zhao from Fudan University of China. Today I'm here as a representative of our team to talk about our work for KAI 2026 on Spark Tales, facilitating cross-language collaborative storytelling through coordinator AI collaboration. So this work is a collaborative effort, and the other authors of this paper include Zhang Peng, Zhou Haoxuan, Huo Xiaojie, Wang Ling, Zheng Wen, Lu Tun, and Gu Ning from Fudan University, as well as Gu Hansu from Seattle, United States. So collaborative storytelling has been widely adopted in children's language and cultural learning, serving as a method to enhance children's language expression and comprehension. So in this practice, a teacher or parent typically acts as a coordinator, providing target vocabulary and a basic story framework. They guide children to use the target language to elaborate on details, adapt the narrative, and extend the story through questioning and feedback. So to maintain a balance between storytelling efficiency and quality, collaborative storytelling is often conducted in pairs, with one coordinator working with 2 children who take turns contributing to the storyline, resulting in the generation of a monolingual or bilingual collaborative storybooks, as illustrated in this figure. In this scenario, collaborative storytelling serves as a key approach to linguistic and intercultural development. So despite these advantages, cross-language collaborative storytelling faces new challenges, among which insufficient engagement is particularly notable. Cross-language collaborative storytelling primarily targets children aged 7 to 11. At this stage, their developing abstract reasoning capabilities can lead to pragmatic misunderstanding, topic breakdowns, and limited interaction strategies during language exchanges. Cultural differences add further complexity, creating obstacles in interpreting pairs, intentions, and reducing willingness to communicate. So, however, facilitation is demanding. Coordinators must judge real-time tasks such as topic steering, vocabulary integration, and question design, all of which require considerable knowledge and skill. At this time, cultural gaps and generational differences in both coordinator child and child-child interaction can cause misinterpretations and communication barriers. Given these constraints, teachers and parents often struggle to maintain effective facilitation, leading to reduced children's engagement in collaborative storytelling. So these challenges motivate us to explain how intelligent systems might support coordinators in reducing workload while sustaining children's engagement. And large language models offer a promising technical foundation for developing intelligent assistance in collaborative storytelling. And first, we conducted semi-structured interviews with 10 teachers via online meetings, each lasting 40 to 60 minutes. The interviews focused on the 3 key dimensions to explain coordinators' current practices, challenges, and the corresponding expectations in this context. So several advantages of collaborative storytelling, like interactivity, playfulness, and effectiveness, have been highlighted by many teachers. Furthermore, teachers typically structure cross-language collaborative storytelling into 3 phases: such as this figure. There are preparation, storytelling, and review. And in preparation, teachers generally collected children's characteristics to support peer interaction. And during the storytelling, there are different tasks, such as the adaptation, the filling task, and the extension. Finally, in the review stage, teachers reflect on interactions and summarize key points for further design. We further analyzed and summarized the prominent challenges these teachers encountered in cross-language storytelling, along with their expectations for intelligent assistance too. So there are 5 findings. The first one is that enable child interaction through feature configuration and matching. And number 2, generate story frameworks and questions to facilitate engagement. And number 3, provide multimodal support for language and cultural comprehension. Number 4, balance engagement through individual and common characteristics. And the last one, track feedback automatically for reflection. And based on these findings, we propose the following design goals for an intelligent tool to assess the coordinators in collaborative storytelling. So we get into these 5 design goals with our model structure. So the overall structure of Spark Tales is illustrated as this figure, which consists of 5 core modules. The first one is called the configuration module. This module enables coordinators to select target vocabulary aligned with the goal of the collaborative storytelling and figure each child's features, including their metadata and such as the cultural background, age, gender, or language proficiency, and also their preferences, such as their preferred topics or some interaction style. And the second module is the second and the third module is individual and common characteristic summarization module. And in the individual characteristic summarization module, it leverages the features based on each child, and the common characteristics module is based on the children's shared preferences and interests. And then the collaborative storytelling support module, it uses both individual characteristics and common characteristics to generate story frameworks and diverse questions, as well as comprehension-oriented materials for the collaborative storytelling process. And the last module is called Review and Feedback module. So after the storytelling, this module can automatically generate the engagement review based on the children's participation, providing the coordinators with a reference to assess the quality of the activity. So we implemented the Spark Tales as a web application accessible via PCs, tablets, and smartphones, supporting diverse usage scenarios and enhance flexibility. So this is our screenshots. And the right panel is visible only for the coordinator, and the left panel is for all participants as a shared screen. So regarding the design goals, we conducted extensive evaluations of Spark Tales into these 2 research questions. So for the first questions, we evaluate the system and its core modules through questionnaires and interviews focusing on the 3 dimensions, the function, performance, and usability, and using the 5-point scale questionnaire. And for the second research question, we evaluated children's verbal engagement across 6 dimensions. Each include an overall mean values as well as a mean value for each language level involved in this study. So overall, Spark Tales enable coordinators to effectively guide children, enhancing verbal engagement and expression, particularly in productivity and lexical diversity. So there are some discussions about our study. We discussed the transforming our coordinator's role in cross-language collaborative storytelling. And the second, we also discussed the children's engagement among these Sparktail's tools. And also the balance of control and visibility within this triangle dynamic is very important in such scenarios. And the last one, we discuss the generalization, like the age adaptation, linguistic context, and other contexts. And thank you so much for listening, and this is our work.
With this lovely talk, I think we want to thank you very much, because you also have to catch a flight.
Yes, sorry.
And we will proceed for the next presenter.
Okay,
so thank you very much.
So if you have any problem, you can feel free to email me. Thank you so much.
Thank you. While we shift the laptops, I would like to welcome Stephen Pilli, and I would like to, okay, let's wait with the diploma. Stephen will be talking about emulating aggregate human choice behavior and biases with GPT conventional agents, and will also receive this honorable mention award for the paper. So please give a hand.
Thank you. Thank you. Oh, I'm sorry, there's some problem with the screen mirroring.
Do we have a plan B? I think we have a plan B.
Mm-hmm. They come out there.
Yeah, it will get up.
Does it work?
Do you want to? It will get up.
Okay.
Do you want to just start?
But your presentation stay in the
Mhm.
my laptop,
Mhm.
not here.
Okay. That's not the one. Okay.
Yes, but no, your presentation stay in my laptop,
Okay.
not here.
Okay. Okay.
Okay.
This one?
Porque bueno. ¿Lo tienes? Ya.
Do you want to start?
Yeah, sure.
Start with something.
Here. Can I use?
Porque lo he quitado yo.
I can ask for the next slide. Yes. And they change the slide. Okay.
No sé, tío. Look there, the screen here. No sé, está la Claudia ahí, pero...
Yeah, sure. Okay. That's the best view. Yeah. Okay. Great. I'm sorry for this. Good morning, everyone. I'm Stephen Pilli, and I'm presenting my preliminary work and findings on how well can LLMs be used to emulate biases in human decision making. First of all, the recent success in the large language models led to a discussion on whether LLMs can be used as synthetic participants, especially in HCI. Few studies explored this idea. They investigated if synthetic participants can produce or reproduce the existing scales, measures, and surveys, especially in decision-making scenarios. Decision-making is an important aspect of human life. However, our decisions are flawed and plagued with biases. Cognitive biases are systematic errors in our thinking. They emerge from our cognitive limitations. For example, status quo effect is a popular cognitive bias where we stick to the default option even though there are better alternatives available. In this specific choice problem here, we have to choose either to remain in the same college or move to the new college. A slightly more advanced version of this choice problem was used to investigate status quo bias. In the original study and its subsequent replications, they used between group experiment design and showed that human participants choose to remain at the same old college, exhibiting strong status quo bias. Recently, few studies administered these choice problems to synthetic participants, and in their subsequent analysis, they found that synthetic participants exhibit these cognitive biases. Most of these studies prompt the choice problem into LLMs using zero-shot prompting. One of the problems with this approach is that the prompts are isolated from the context, and as these choice problems are extensively available in the training data, we do not know if the observed behavior emerged from the training data, or do they really have a model of human biased decision making. So we made a very preliminary progress or effort towards addressing this issue. So decision-making doesn't occur in isolation. It occurs within a context. So contextual factors like cognitive load can make us think less and make us more prone to biased decision-making. So we shortly call this specific dynamic load-bias interaction. So if synthetic participants can reproduce this specific dynamic, we have some preliminary evidence that decision-making in synthetic participants is not occurring in isolation, but it is contextual. So to investigate this specific load bias interaction, we chose task-oriented dialogue. Our decisions can be biased even within the conversational environment like task-oriented dialogue. However, in this specific configuration, the choice outcome can potentially be influenced by the prior dialogue. As you can see here, the prior dialogue is acting as a context to the choice problem. Therefore, we can test if the cognitive load arising due to the context or the prior dialogue can potentially influence the cognitive bias observed in the subsequent decision making. So to do that, first we have to establish a baseline. So these are our hypotheses. So we investigated if status quo bias occur in task-oriented dialogue. Second, we investigated the load bias interaction in human and conversational agent interactions. And third, we investigated if synthetic participants can reproduce this specific load bias dynamic. This is our human experiment method. To test our hypothesis, we manipulated the prior dialogue complexity of the dialogue, the task-oriented dialogue, and observed the aggregate human choice behavior over the subsequent choice problems. In a between group experiment of 1,100 participants, we randomly given a simple or complex prior dialogue to each participant. The decision outcome over subsequent choice problems were analyzed to determine the load bias interaction. 3 choice problems were adapted from famous Samuelson-Zeckhauser's original study. These choice problems were successfully reproduced in recent replication studies as well in 2021. Coming to our results, This forest plot here shows the proportion of participants resisting to change or showing status quo bias, and this is measured in effect size. So on the x-axis, you see the effect size, the coherence age. So in this plot, the no load condition is when the prior dialogue is simple, and the load condition is where the prior dialogue is complex. We compared our effect size with the original study and found that status quo bias do manifest in task-oriented dialogue. However, the choice problem did not find any load bias interaction. The effect size is almost same even when the effect size are close to, sorry. Effect size are close to 0. If you can notice that from the second choice problem here. Next, we tried to see if these results can be reproduced in agent experiment. Even though these are null results, they're very important for this specific experiment. I'll show you how. So in the agent experiment, to create a synthetic participant, we borrowed the chart transcripts and demographic information of each human participant. The option selected by the human participant for the choice problem in the human experiment was excluded from the chart transcript. So the chart transcript contains only the prior dialogue, human response to the prior dialogue, and choice problem, but not the human decision or the choice problem. On top of this transcript, we added a human likeness prompt for the synthetic participants. You can see here the human likeness prompts. We tested 3 human likeness prompts based on the explicitness of the bias investigated. In the bottom level, they were told that they were just humans. The synthetic participants were just humans, so act as being human. And in the top level, they were told that they were susceptible to status quo bias, so act like one. So now let's see what happens with this. So here we are comparing the forest plot of agent experiment with the human baseline. On the leftmost column, you find the human baseline. We ran this experiment across 4 different language models. In our human experiments, we did not find any load bias interactions. So the favorable case amongst these agent experiments are those which do not show the load bias interaction. Oh, sorry. Yeah. To quickly summarize the results, if you look at the GPT-5 and GPT-5 mini, you notice that they fail to reproduce the observed load bias interaction. The deviation from the regression from difference in the regression is completely large in terms of GPT-5 and comparing to the agent experiments to the human baseline. So next, when we tell the agents that they are quite susceptible to status quo bias, that is in the human likeness level 3, we found that the agents deliberately show bias even where there is no bias in human baseline. Let's say for this instance, you can see that there is no bias found in the human experiments, but you can clearly observe that agents were showing some bias here. So, but lastly, what we found was that like GPT-4 and GPT-4 mini were able to closely reproduce this human baseline. So the key takeaways from the whole experiments that we did was that this is quite a preliminary study, and we found that the status quo do manifest in conversational agent interactions, and dialogue architects, especially in the HCI community, must take this into account. And the load bias dynamic can be used to validate LLMs to be used for synthetic participants. Future work should also consider more bias for broadening the scope and the generalization of the this area. Thank you.
Thank you very much. We have a little bit of time for questions, so please raise your arms very high so that the microphone can run to you. Okay, I'll run with the questions then.
Yeah, sure.
Based on your study, how do you see the perspectives for what how synthetic participants can be applied?
So this specific study is quite basic. Like it's just a direction that we are trying to set up. It's quite preliminary. So based on the preliminary evidence, I could say that if we can do further experiments on more biases, like framing bias or something, we'll be able to concretely say that these participants can be used, synthetic participants can be used in HCI studies, actually.
Okay.
Yeah.
Okay.
So just one quick teaser. Like we try to reproduce this specific this specific method using framing effect, and we found some interesting results. Please keep in touch, or I can provide you with the future papers that we come with. So we are publishing soon. Thank you.
Thank you very much. So next speaker, we invite Masahiro Kono to first complete the challenge of connecting the laptop to the projector. And once this is successfully accomplished, he will be talking about no pixels left behind, filling gaps in anime colorization.
One moment. Please. My friend is on there. Would you like to pass here? One moment. Is it ready? Es que esta no es la suya, la que estás viendo tú ahí. Esta es la que la voy a tomar. Vale, vale.
I think I can start.
Please start.
Okay. So
The color is okay. The color for.
yeah, that's okay. That's okay.
Okay. Sí, sí, lo veo, pero dice que está bien. Pónselo en pantalla grande.
Okay. I think I can start. Hello, everyone. My name is Masahiro Kono, and I'm from the Igarashi lab at the University of Tokyo. Today, I would like to present my work, No Pixel Left Behind, Filling Gaps in Anime Colorization. And here is the outline for today's presentation. First, I'll begin with the introduction and background. In anime shiage, or finishing, colorists usually fill each enclosed regions with a flat color using the paint bucket tool. However, this process often leaves tiny enclosed areas unpainted. We refer to these as unpainted gaps, shown in green in this figure. These gaps often appear in sharp regions, such as hair tips, and are tedious for artists to detect and fill manually. To address this issue, we propose a production-oriented support tool for anime colorization. This slide reviews two representative directions in related work. First, automatic line art colorization has been studied for many years, and recent approaches are mostly based on deep learning. However, small regions remain difficult to predict accurately. Second, research grounded in real anime production workflows remains limited. As a result, there is still a gap between research and practice, and unpainted gaps are not yet well addressed in production. Next, I would like to introduce the methods and tools to handle unpainted gaps as identified through our formative study. Based on our observation, professionals commonly rely on three approaches in Clip Studio Paint: the blacklight method, leftover pen, and enclose and fill. First, the blacklight method helps with detection by temporarily replacing all colors with black so that unpainted gaps appear as white dots. Second, the leftover pen helps with correction by filling unpainted areas along the brush stroke with a specified color. And third, the enclose and fill also helps with correction by filling enclosed regions inside a lasso selected area. However, even with these tools, colorists still need to repeat 3 manual steps: detection, zooming, and color selection. We aim to reduce this burden. Now, let's move on to the main part, the overview of the features of gap fill. The gap fill interface consists of 5 main interactive features. First, the unpainted gap detector automatically detects enclosed unpainted regions and highlights them with circles. This reduces the effort required for manual detection. Second, automatic color suggestion temporarily overlays each detected gap with a suggested fill color. This reduces the effort required for manual color selection. Third, hover-activated pop-up magnification allows users to inspect the local result quickly without the need of manual zooming in and out. And if a suggested color appears incorrect, the user can drag inside the circle and correct it by selecting a nearby color through a color picker-like interaction. And finally, if the suggestion seems to be correct, the user can drag outside the circle to apply suggested color in batch with a brush-like gesture, or confirm all predictions at once using the Apply All button. Next, I would like to briefly explain our novel automatic color prediction method. Our key idea is to predict colors indirectly by learning region-to-region correspondence, which makes the model more robust. This design is motivated by the flat color nature of anime images and by the fact that unpainted gaps themselves are independent of any specific colors. In other words, instead of directly regressing colors, the model estimates which surrounding large region is most likely to share the same color as the target gap. Now, let's move on to the evaluation and discussion based on our user study. To evaluate usability, we conducted a user study with 13 professional anime colorists using custom-made painting software similar to a real production environment. For a fair comparison, we used near-symmetric anime images containing hair and split them into left and right halves. The study mainly consists of 3 types of tasks. In task A, participants colored real line art from scratch. In task B, they detected and filled intentionally set unpainted gaps in almost fully colored images. And in task C, they subjectively evaluated batch applied color predictions for small enclosed regions. This slide summarizes the usability results. Quantitatively, gap fill significantly reduced completion time in task B for both images. It also outperformed the baseline in terms of missed gaps, leaving 0 remaining gaps. And qualitatively, participants generally rated gap fill as more practical for adoption than existing tools, especially in final checking scenarios like task B, where in task B, preventing missed gaps is particularly important, and in this setting, its visual support features were especially well received. By contrast, in more general colorization scenarios like task A, there were larger individual differences. One possible reason is that existing tools can be more efficient for filling large areas and multiple gaps at once. This also led several participants to suggest that gap fill should be used together with existing tools rather than as a replacement, since each has its own strength. Now, I would like to discuss an interesting insight about the role of prediction accuracy in tool usability. This relationship seems more complex than the numerical results, as participants express diverse views on accuracy. Some said that AI mistakes are acceptable as long as they can be corrected quickly and the user stays in control. Others, however, said that even a single visible mistake could reduce their trust in the remaining outputs. They also noted that the acceptable level of accuracy depends on the production deadline. This suggests that tool usability depends not only on prediction accuracy, but also on manual control, trust in AI, and the production context. And in the first place, we hypothesized that for tiny regions, there may be more than one visually acceptable color choice. So in task A, we observed some cases where gaps were filled with different colors, yet no visible differences was produced, as shown in this figure on the top left. This suggests that a single correct answer may not always be necessary. On the other hand, at the same time, the subjective evaluation in task C was not perfect, with a median score of 5 out of 7. Here, participants especially pointed out that salient regions, such as the pupils, still require correctness. Taken together, these findings suggested that accuracy itself may need to be reconsidered in a more context-sensitive way. Finally, I would like to conclude by summarizing our contributions and outlining the future work. Our contributions are fourfold. We conducted a formative study and identified the challenge of unpainted gaps, proposed gap fill as a production-oriented support tool, introduced a novel deep learning-based color prediction method for small gaps, and evaluated the proposed tool through a user study while obtaining new insights into creativity support tools. For future work, we plan to improve prediction accuracy in important regions such as the pupils, develop new evaluation metrics for accuracy based on perceptual quality, and develop the system toward practical deployment with stronger integration into existing tools and workflows. And thank you for your attention.
Thank you very much. Again, we have a little time slot for a question. There's a question here, and the mic is rushing. Thank you.
Hello, can you hear me?
Yes.
Thanks so much. Wonderful talk. I'm a little curious. You showed this very particular workflow that requires a lot of careful detail, and you had one small step being automated. Now, I can imagine in the future, like your UNet model could predict automatically coloring the whole thing, right? As things move towards like things are automatically colored, did you get any sense from your participants about their perceptions of what that would be like? Like as their workflow would move more towards editing something that's already there versus like manually doing it?
Sorry, can you say the question again? Sorry.
Yeah, apologies. It was a little fast.
Yeah.
It seems like right now the model was just predicting small changes to this image that they were touching up.
Mm-hmm.
You could imagine it could automatically, say, color a whole image. Do you have a sense of whether your participants would view that favorably, unfavorably? How might they view that? Or do you know? Or would you have a sense of that?
So you mean that, do I have any idea to like fully color the line art?
Yes.
Yeah, that's a good question. So there's like many previous research related works that try to colors the whole line art, but the accuracy for large regions, it's quite good, but for these kinds of small regions, it's always like not that good. So that is a really like difficult point. And so for my work, I focus on those kinds of small regions. And yeah, does it make sense or like?
Yeah, that makes sense. Yeah, thank you very much.
Thank you for your question.
Thank you very much, and we have to conclude here, so thank you very much.
Thank you.
And now we want to welcome Jiale. And in the next talk, we will be hearing about how to facilitate group ideation with AI-mediated idea sharing.
Back to the first page, please. Oh, here we go. So good morning, everyone. I'm Jiale from HQST Guangzhou, and it is a great pleasure to be here presenting our work, GraphMind, facilitating group ideation with AI-mediated idea sharing. So let's get started. Yeah, group ideation is a common practice in daily collaboration, and there are two common settings for conducting these activities, the group brainstorming and individual brainstorming. Well, each setting has its own pros and cons. In group brainstorming, people idea together and usually use a shared work canvas to exchange ideas. This instant idea sharing can enable synergy, supporting the group in building on each other's idea and sparking new ideas. However, when our thoughts are being transparent, it may cause social influences, such as evaluation apprehension. People may anticipate others' judgment of their ideas, and this anticipation may impact creativity. The individual brainstorming, in contrast, encourages group members to idea separately and consolidate ideas at the end. This solitary ideation process could alleviate evaluation apprehension, but it comes at the loss of losing synergy, since little thoughts are shared during the process. So the idea sharing seems like a double-edged sword. Therefore, existing hybrid approach suggests conducting both individual and group brainstorming well in a single session. But at any given moment, participants are still affected by either weak synergy or evaluation apprehension. So, above all, there's a need to explore a novel setting that moves beyond the existing dichotomy, one that enables synergy while mitigating evaluation apprehension at the same time. Inspired by the concept of an AI mediator in asynchronous collaboration, we aim to explore whether AI-mediated idea sharing could help resolve this dilemma. By enabling controlled idea sharing, group members may only receive the necessary team knowledge at the appropriate time. So, driven by this concept, we identify three challenges. First is individual ideation state inference. We should know what kind of group knowledge could benefit each member. Second is idea selection and assistant generation. It is about how to select relevant ideas and generate assistance content. Third is assistant delivery. This is how to present assistance without disturbing users' ongoing ideation. So in response to these three challenges, we designed the following system pipeline. Inspired by the dual pathway theory, we first introduced the ideation state inference. We identified users' ideation states from the perspective of divergence. We first rank each individual's ideas by internal similarity using a re-ranking model. For those whose idea similarity is higher than the group average, their thinking may lack diversity, so they may benefit from the flexibility assistance. For those whose similarity is lower, persistent assistance may be more appropriate. For those whose similarity falls at the median, we can just let them to continue their own thinking without interference. So the second step is the shared idea selection. For users needing flexibility assistance, the system retrieves the idea from others that is the most different from their own. And for users needing persistent assistance, the system identifies the most similar idea from others linked with the idea from this user. For users whose diversity is moderate, the system only highlights their own most distinct idea to encourage further exploration. All three sharing processes are triggered when the user temporarily stops ideation activities for more than a threshold number of seconds. Ideas are delivered following a right-dot interaction patterns to prevent interruption, and the indicator is designed as a carrier pigeon to convey the concept of idea sharing. I think here's a video. Could you play for me? Yes. Maybe not. It is a technical issue. So to evaluate GraphMind, we conduct a between-subject user study. The experimental condition used GraphMind, while the control condition used traditional group brainstorming, both for the same long group ideation session on the same topic. We recruited 60 participants and divided them into 2 conditions with the same academic level distributions. So corresponding to our research questions, we collect the following data, and following this procedure, now we will discuss it in details. So the first RQ is how might GraphMind affect group ideation performance? So the most direct measures are idea quantity and quality. We define quantity as the total number of ideas generated per group, and the quality as the number of semantically distinct clusters, which is also known as the originality. So the results show that the experimental condition produced more ideas and idea cluster per group than the control conditions. We also analyzed participants' activity levels during the session. So we calculated as the sum of node creation and editing behaviors in the system. As shown in the figure, participants in the experimental condition perform higher ideation activity throughout the session. Further examining the type of AI assistant received prior to the ideation activity, we found that after receiving the flexibility assistance, participants were more inclined to create new nodes, while edits to existing nodes occurred more frequently after receiving persistent assistance. This aligned with our motivation using the dual pathway theory. For RQ2, how might GraphMind affect synergy? We use a synergy perception scale adapted from the knowledge sharing scale. Results show no significant differences between the 2 conditions, indicating that GraphMind enables users to perceive a similar level of synergy as in the group brainstorming. Through log analysis, we also identify clear cases showing how user benefits from the shared ideas. And for the RQ3, how might GraphMind affect evaluation apprehension? We used an evaluation apprehension scale based on the brief fear of negative evaluation scale. Results show that participants in the experimental condition rates lower than the control conditions. So based on the above result, we can say GraphMind enables users to explore ideas with reduced evaluation apprehension while still gaining synergy from the group's collective knowledge. It has ultimately improved the group ideation performance. Our interviews surfaced many responses that further support these conclusions, but due to the time constraints, I will not discuss them all in detail. But I would like to share 3 interesting findings. So the first is the importance of the timing in ideation sharing. Group ideation in synchronized collaboration with a relatively high cognitive load. So the interruption during a user's active thinking incurs a cognitive resumption, leading to dissatisfaction. So it is ideal to be only triggered when ideation is in a blockage. And the second is the system should control the content volume of the AI-generated assistance. In our interviews, participants described the ideation task as a time-pressured, and they were generally not willing to read lengthy assistance content. In many cases, a simple hint or short phrases were more preferred. And third, we want to emphasize the role of visual design. So it helps convey the presence of teammates and a sense of collaborative engagement using the metaphor of pigeon, as participants noted that even without closely examining the specific content of the suggestions, they could still perceive the concept of idea sharing through the pigeon metaphor. While we still have some limitation and future work to do, for example, the rigor of the user study, the accuracy of the intervention timing algorithm, and potential personalization features. So that is all we want to share in this presentation. Thank you for listening. Any questions, welcome. Thank you.
For a very timely and efficient talk.
Yeah.
Questions, please. I was wondering, in terms of the rationales for the design,
Yes.
in your design, there are some assumptions about when it's good to. Sorry.
It's clear.
You were allowed to ask questions before, unless you missed it. I mean, the thing about when the system intervenes and the rationale for the design, so you have kind of an automatic timer. I mean, it's very much based on implicit interaction, right? When the system intervenes.
Yes.
Can you provide some rationale for that, or pros and cons for this this approach?
Yes, as noted in the limitation part, the timing is very important. Well, as the initial step of this study direction, we are not examining very clear of the timing. So currently, we use the stop behavior. For example, if the user stop operating the system for at 15 or 20 seconds, we will think it may encounter a blockage, and we deliver our assistance. But sometimes it works, sometimes it's not, because in our interview, some user may just stop for thinking, right?
Exactly.
So in our paper, especially in the limitation part, we suggest in the future work, maybe we can analyze the content user just created. Because if the content seems a little bit similar, maybe they are just running out of mind. So, yeah.
Or the user could trigger the support more explicitly.
Yes, yes.
Okay, good. Let's shift the laptops while there's still a bit of time to ask questions. So if you unplug and we invite the next speaker to the stage.
Yes, that'll be fine. You can find me later in the session, after the session. Thank you all.
Okay, thank you.
Yes.
So now we have actually the first paper being presented because we had a little swap. So I'd like to welcome Yuwen Lu, presenting the paper called Crepe, a mobile screen data collector using graph query. And while we exercise the connecting to the display, I'd also like to put this honorable mention award
All right.
looks tasty. Please go ahead.
Thanks. Good. I just turned it off. I'm turning it back on. Let me pull up my notes. Well, I've been waiting for this presentation for 4 to 5 years because this is one of my first projects I worked on when I was a PhD student. Now I'm graduating this year, so it took a little while to get this out. But, well, thank you for the award. I don't really know why I got the award. This paper, for context, was rejected twice from WIST. And in between them, I missed a mobile HCI deadline, missed a CSEW deadline. So if you're submitting paper and get rejected, don't worry about it. You're going to get there. Well, as I said, I started when I was a first-year PhD student. It was before ChatGPT launched. So if you go to the repo, you're going to see all handcrafted artisan code with no AI agents. If you run into bugs, that's the issue. This paper really, it's called Crepe. It's a mobile screen data collector using graph query. It's not really collaborating with AI. That's the title of the session, but it's helping us to scrape data from participants' phones and see whether we can use this data for a variety of different purposes that I'm going to talk about. So when I say mobile screen data collector, what I really mean is we scrape data, collect data from end users' phones, like if you're using your phone right now. Potentially, we can have the app installed on your phone and collect some data for you. And why do we want to do that? Let's think about this. Oh, I want to thank my collaborators that worked on this paper together first, before I get into the meat of the paper. Some of them started working on this as a sophomore, and now they're graduate students at Berkeley and other different places, so it really took a little while. Okay, so collect data. Why do we want to collect data? Let's think about this scenario that you're scrolling through Instagram, and then you wonder, oh, I see a lot of ads every day on Instagram stories. What are the exact ads I'm seeing every day? Collecting this kind of screen data has a lot of use cases, as I said. As a user, it raises your awareness of the algorithm that is used to target your attention. And once we collect data to understand the algorithm, we can do auditing on top of it, try to figure out, for different types of users, what are the variety of different ads that were pushed to their story feed. And then the other thing that we can do now that AI is getting more capable is we can use this data to train personal agents. Once we know the data is the kind of data that shows up on your screen and the actions that you do with them. If you want to collect Instagram story ads data, you go into Instagram API platform. The only ads API that Instagram provides to developers is for you to programmatically create and publish ads on Instagram. And if you asked ChatGPT, or in this case, Google AI mode, there's no real API for you to put in your profile, your ID, and then get the list of ads you've seen in the past couple weeks, days, or whatever time period you're interested in. So to understand this kind of screen data and collect from your phones, there's this project called Screenome project at Stanford that basically takes screenshots at intervals by installing like a scraper on your phone. This is the closest that we can get for what we want to do, but a really big limitation of this, it takes screenshots at set intervals. So here I'm simulating a timestamp or like a time scale of you on your phone. If you take screenshots at a given interval, you cannot guarantee that you're always collecting the data that you want. So for the yellow orange-ish triangle that I have here, these are the missed data collections that took screenshots, but not exactly the data we were trying to collect. And this is the optimistic scenario. Honestly, like if you do a lot of different things on your phone, it's really hard to guarantee that you're collecting the right data. And nowadays, we can use visual language models to take screenshots and ask questions about it, but there are potentially privacy risks of sending all of the screenshots from your participants' phones to a cloud server and asking a question about it. What if I'm entering my password? And the other question is when to check all of these. The Screenome project uses the set time interval as their trigger, but that's, as I said, really inaccurate. And if you use a VLM locally on your phone or on a server, in both scenarios, it's really costly. Like running inference for these models are, pretty resource constraining, especially if you do local, which is what Apple is trying to do. But we haven't seen a lot of success for it yet. So that's why we designed this thing called Graph Query. The goal of it is really, if I want to collect this piece of ad sponsored ad account name like Apple here, I want to collect the target data. And I only want to collect the target data and nothing else. So how do we do it? We designed this graph query to turn a screen into a UI snapshot. The screen is what we see on the left. What we have access to is Android Accessibility API, which we kind of hacked and turned, just like the top right here, we turn a screenshot into a UI hierarchy tree, have all of the elements and their relationships. What we do in the UI snapshot is to augment this tree accessibility tree structure to include information about the attributes of each element on the screen. For example, the button has a class of button, the button has a text of sponsored, and we add the spatial relationship between elements on the screen. This basically makes the accessibility tree a little more information rich so that we can do query on top of it. What we can do is, if the user say, I want to collect Apple, we can try to create a query that parse through the accessibility tree and hence the UI snapshot and identify only the orange Apple node that we have in this graph. It looks something like this. You can look into our paper to understand how it works, but basically we can combine a couple of different attributes of this UI element and then make up a unique graph query that can, as I said, identify the target data and only identify the target data and nothing else. So an example that we have here is once we have this graph query, if we see another ad that shows up in your Instagram story feed, we're able to collect the brand name for the sponsored ad. But if you are browsing any other screen like the Nike app here, we don't really retrieve any result because the graph query doesn't fetch any result in this screen structure. Okay. On top of graph query, we built an app called Crepe. That's the meat of this presentation. And here I want to give you a quick demo of how it works. Basically, we care about the researchers who are trying to collect the data. How do we support them to define the data we're trying to collect? And for the participants who are participating in this user study or data collection study, how do we support them to very easily install the data collector on your phone and then start scraping immediately? I will start playing here. This is the view for researchers. So as a researcher, what you can do is to create a new collector using the button here. You can specify the start date, end date, and the app you are trying to collect from. So here we're specifying 2024, which is when I first submitted this paper to WIST. And then you define an app. And what you can do is we use a programming by demonstration paradigm, like interaction paradigm. So instead of, say, describe the data that you're collecting, what you can do is to just go into the app and then use the widget here to say, I'm drawing on top of the screen and just clicking on the data you want to collect. And then Crepe is going to do all of the data parsing, graph query definition in the backend. And then once the user confirms that this is the data they want, they can add a description. So here I'm going to say sponsored ads on Instagram story. And then I come back here, the data is added. And then I add a description for this data collector, and what Crepe does is it gives each collector an ID, and then you can share this ID with your participant, and then you're gonna see the data flowing in on the database that you set up. So as a participant, so switch of view, this is a participant now. If I want to, okay, let's see. If I want to add a collector to my app, what I really have to do is to use the add existing button here, paste in the collector ID, and it's just gonna start running on your phone when the collection start time is reached. Okay, that's the demo. I'll try to figure out how to go to the next slide because YouTube is kind of wonky on this. Okay, we did some evaluations. We evaluated 3 scenarios, but here I'm only showing the collection accuracy. It's really hard to guarantee 100% accuracy rate on this kind of data collection. We were able to reach F1 score of over 96%, which is very happy for us. You can look into our paper for more details. We basically collected on 3 different apps, Instagram, Uber, and Chrome, for different types of data to make sure we have good coverage. But this approach has some limitations. So the UI layout might shift, and our app really operates under the assumption that the data we're collecting is in association with all of the other elements on the screen. So once the UI layout shifts, it's hard to maintain that consistency in the data collection. And then it is, as I said, well, VLM are pretty good. This is less flexible than a VLM in the case that if the UI layout shifts, if you ask, based on the screenshot, what is the sponsored ad here to a VLM might still answer the question correctly, but once the layout shifts, it doesn't answer as consistently for our app in this case. But the thing is, we really think our app and VLM can work hand in hand by defining a graph query as a trigger for taking a screenshot and then sending that screenshot to a VLM in the future when the inference cost is lower. And then we're currently limited to textual data, while it's mostly like an implementation detail. We can add screenshots, image-based capabilities very easily. A lot of use cases, as I said, can be used for this kind of app. Break the data monopoly, that data is only possessed by the companies. We can train an AI assistant for the user based on their own data. We can do UI automation on top of it. Just skimming through because we're running out of time, but here's the end of my presentation. Thank you.
Thank you very much. So I'd like to invite Karin to set up the laptop for the next talk while we invite for questions. People have not had their coffee yet this morning, but now you just had a crepe, right? Okay, I'm curious a little bit about the next steps for this work. I mean, you were pointing to different use cases, but how will you actually proceed also more towards those? You can borrow this mic.
There are a lot of things we can do with this. Collecting data is probably the first step, and I've been talking to folks to make sure that we extend this app to make it actually production ready to collect data from participants in various scenarios. There are folks who are talking to at Penn State that might use our app to complement their current data collection efforts, and then some postdocs in our lab are trying to collect data using this app. So really, I think a big concern is privacy and how do we ensure the data is secure. We're trying to use state-of-the-art industry-grade databases that have protection, privacy, security baked in to avoid doing some of these things ourselves. But really, data collection is going to be our next steps. And once we have the data, hopefully someone is going to pick up the data and train a model, or we can do it ourselves. But I'm graduating, so I don't really worry about it. Thank you.
Thank you very much. And don't forget the award. Right, everyone. So we have with us here Karin Breckner. Warm welcome. And now it's about framing collaboration, how human-human principles can translate into human AI realities. We cannot hear you.
Manu, ¿tienes abierto el micro? Hola, hola. Hey, hey.
Oh, no. Okay. Okay, hello. My name is Karin Breckner, and I'm presenting our paper titled Framing Collaboration, How Human-Human Principles Translate into Human AI Realities, with my co-authors Thomas Neumeier, Marc Streit, Martina Mara, and Miriam Augstein. Our work is motivated mostly by the rapidly increasing research interest in human AI relations, but specifically one term is increasingly popular. As you can see on this graph, the publication counts where human AI collaboration is used already in the title increased drastically in recent 10 years. And we found that a lot of different settings were even described in such studies. This made us wonder whether humans and AI actually collaborate in those settings and what such collaboration is in relation to human collaboration. This led us to two research questions. And the first one is, what are the key components and themes of human-to-human collaboration in scientific literature? And the second one addresses the current understanding of and implementation of human AI collaboration. To address these research questions, we employed a multi-step research pipeline, combining human and LLM-based knowledge. The first row of this chart shows the manual analysis of literature on human-to-human collaboration, yielding 40 components as a framework for the later LLM-based analysis. In the first LLM-based step, a GPT-4o mini assistant was instructed to generate a textual definition and guideline for each of the 40 components to facilitate extraction for the later models in these subsequent steps. Sorry. In the second LLM-based step, two different models were employed to combine generation and reasoning knowledge of different models. They used the definitions and guidelines of the previous step to extract candidate sentences that they found representative of the respective component of the entire corpus of literature. And in the third step, then another reasoning model was employed to evaluate these sentences and determine whether they align with the definitions and guidelines of the respective components, and if they were valid, to determine whether human and AI were involved both in a balanced way, or whether one party was involved more prominently. Oh, sorry, this was the second and third step. Overall, our work offers several contributions. First, we provide a thorough cross-domain conceptual foundation for the later LLM-based analysis and a thematic framework of human-to-human collaboration in scientific literature and across different domains. Second, we can offer hands-on learnings on LLM-based literature analysis. Third, we map component coverage and the involvement of humans and AI in each of the components based on a large body of literature on human-AI collaboration. And finally, we could derive several empirically grounded implications and an agenda for future research. Let's start with human-to-human collaboration. We found that even in this context, there was no universal consensus on what collaboration is actually. For this reason, we decided to conduct a systematic analysis of literature across different domains using JSTOR, ERIC, Scopus, and PsycInfo databases to obtain both a interdisciplinary perspective and also avoid getting stuck with our own background in computer science. We searched for a definition of collaboration in publications abstracts. This search yielded a total of 141 items across databases, of which 60 were finally included in our analysis. One researcher then read all the articles and screened for possible descriptions of components of collaboration, and 40 of them were then used for the framework. The researcher read all the articles again to re-evaluate the presence of all components. Right, and then we discussed in groups of researchers to obtain the final framework of 7 sub and 3 main categories. The 3 main categories address the collaborative activities and dynamics, including interaction-oriented and goal-oriented activities. Then we have the sharing and collective purpose, where there are shared assets, the ownership, and the goals and purpose that lead the collaboration. And in the team and relatedness main category, we have team constellation and social aspects. So it's more about the collaborators themselves rather than the activities or the tasks. We additionally discussed the perspectives of Zhao relating to the interaction dynamics in collaboration, McGrath's task demands, and Tuckman's model of temporal progression for a more holistic view. For example, components in the interaction-oriented subcategory mostly reflect the interaction dynamics. Then the goal-oriented activities and the shared assets mostly relate to McGrath's perspective. And the ownership and social aspects represent a temporal progression according to Tuckman. Finally, we were most interested in the current understanding of human-AI collaboration in scientific literature. And we employed the 3-step approach, which I briefly explained earlier, which ultimately yielded a number of candidate sentences that reflect the different components, and also the assessment of the involvement of human and AI participants in it. One researcher additionally read all the extracted sentences to have some additional insight and a thematic analysis of the individual components. For the results, this table shows the framework again for derived from human-to-human collaboration in the first 3 columns, and the results of the human-AI analysis in the last 2 columns. The overall bar length shows the count of the publications that mentioned where this component was found, and the colored segments indicate the involvement. So the middle colored bar segment is the balanced involvement, and the left and right ones are the more prominent human or AI involvement in the respective component. Right, overall we can see that for one, the models had quite a similar picture, but also that human AI collaboration was not that different from human to human collaboration. However, there was still some differences, of course. For example, there was a sparse coverage of consensus building joint planning and joint goal setting, and this aligns with existing research which found that humans did not accept AI in the coordinator team role, as they expected a coordinator to have social and emotional skills, and AI was of course not capable of doing this, even though it was able to produce emotional output. And for this reason, we also have sparse coverage of ownership and social aspects, where you can also say that this might require some skills that humans have. Then for the conceptual perspectives, they are also quite, at least throughout the concept, also applied. And interestingly, there's an asymmetric involvement in the interaction dynamics, for example, in information sharing and adaptation and learning. There might be the AI sharing information without anything coming back from the human, and also one of the participants might adapt to the other without mutual learning and adaptation. Then our findings lead to different opportunities for future research, and I will just mention some examples. So one could use our framework to investigate the concept of human-AI collaboration of different perspectives in more detail. For example, including temporal progression over time, as a collaborative setting usually requires a development over time according to Tuckman. Then you could also investigate richer team constellations, as most current human-AI settings have exactly one AI and one human. And of course, in groups of humans, there might be additional group dynamics to investigate. And also, it might be interesting to investigate different task types, as right now it was just a very general concept of human-AI collaboration. Then it might also be interesting to study the human perception of AI in different collaborative settings. And finally, we started our analysis by investigating human-to-human collaboration and deriving a framework from that. and then investigated human-AI collaboration, and it might be interesting to do that in the reverse order, as our approach might have constrained the analysis of human-AI collaboration to only the components that are found in human-to-human collaboration. So one might just start at human-AI collaboration and then find what is different in the other way around. Yeah, then thank you, and if you have any questions.
Thank you very much. So I'd like to invite Hawaii Su to start setting up for the next talk and kind to unplug while there is time for the microphones to reach a person with a question down at the front here, please. Maybe you can come here to this mic for the question.
Hi, thank you, Karen. That was a really interesting presentation. Kind of two questions. I didn't pick up how you defined balanced in the way that you looked at the bars. You had the balanced in the center, and was there a definition of balance that I missed? And the second question. And the second question is that you started off by questioning whether collaboration is really happening, and I'm wondering whether you came up with an answer to that. Is anthropomorphization appropriate, or is it a bad use of language?
Does this microphone work? Yeah. So I'm not sure I understood correctly, because it was a bit difficult to just have it acoustically. So your first question was whether there was a definition of what was balanced?
Yes.
We don't have a unique official definition of that, but we determined that if, for example, both humans and AI share information at the same time, and this was indicated in the sentence, then this was balanced involvement. Also, if both communicated, if both adapted to each other in a process, this was balanced. However, if, for example, information sharing, this was, as I said, mostly the AI providing information, and the language model determined it by itself then whether there was balanced involvement or not. Of course, a human also checked that, but it was done by the language model.
So can I probe a little further, if there's a moment longer? Does that mean you're suggesting balanced combinations are equivalent to collaborative combinations, and that where there's imbalance, it's not collaborative? Is that reasonable to take from what you said? I
wouldn't say that in general. I think there can be one-sided components in collaboration also. But of course, if there's a large difference in comparison to human collaboration, we might just observe this difference.
Okay, and if there's time, the question about whether it's too anthropomorphizing would be interesting. Thank you.
I didn't get the...
Maybe you can talk.
Yeah, maybe we can discuss it later.
Yeah, that would be great. Thanks very much.
Time.
Thank you very much again. So we are kind of ready for the next talk. Or we were kind of ready for the next talk.
Something changed now when you unplugged? Yeah.
Thank you for waiting, the technical issue, and good morning, and thanks for coming. Today I will present our work, AI as an agent and collaborative space, exploring the role of generative AI in small group synchronous and asynchronous collaborative dynamics. And my name is Wei, and we have also some co-authors, Ahmed Karufa, Agnes Sangoman, and Vasilis Verkokrakos. We are from the Open Lab at University of Newcastle in United Kingdom. And let's start. So our research comes from the question, generative AI is changing how people work individually. So how does it shape the teamwork? To answer this question is a little bit complex because actually generative AI is everywhere in the teamwork, but correctly it's mostly like a designed for one users and one AI, but actually in reality, the collaboration is always multi-people and sometimes multi-agents. So the collaboration is not just like lots of the individual work together, but it is very shift quickly and it needs its collaborative dynamics. So in this coordination, the negation, the shared understanding, and of course the shared responsibility. So our research question become, how does generative AI influence collaborative dynamics in the small group work? To make that, we have some dimensions in the collaboration dynamics. Firstly is the information flow, that is how knowledge and clues going. And then the role negotiation, that is how responsibilities shift. And last, decision making, how teams evaluate and coverage on outcomes. And we also use distributed cognition as our theory lens. So traditionally, the cognition is always in our brain, but the distributed cognition thinks the cognition is not just in our brain, but also in the people, that is the team, and also the tools, which is generative AI, and also the environment. And we use that because it can perfectly fit the dimensions we found in the collaboration dynamics, that is information flow, the role, and the decision making. And then let's move to our study. So we have two parts of the study. The firstly is the observation, that is for the synchronous collaboration. And then we also have interviews for like a more widened use of the AI in the daily collaboration in the asynchronous scenario. And I will introduce them one by one. So firstly is the observation set up, and we have two kinds of the settings. One is online and one is in person. So for each group, we have 3 participants, and only one of the participants can use the GPT-4 as the input. We do that is because we want people to talk, to discuss about their work. But the AI output is visible to all. That is very convenient for them to use the information from the AI. And we gave them a design task, which is an educational game, and it is based on some culture. The culture is beyond the participants' background because we want them a need to use AI support. And we don't ask our participants to have like a fixed output format, so they can choose like a document or diagram or artifact, whatever they want to finish this game design. Because the outcome is not very important in our study, we focus on the cooperation. And for the interview, we have 9 participants and 45 minutes semi-structured interview for each one. And we focus on how they use generative AI in their real group work, like when they are doing their report writing in the group, the coding, and also the design work. So now let's move to our findings. We have some very interesting findings, and firstly, I will introduce our observation findings. So firstly is information flow in human AI cooperation. So we find people use the prompt to control the AI, of course, and we find 2 kind of patterns of it. So one is collective prompting, so people gather discussion, and when they have a common
decision, they use the prompt to control the AI and ask for the feedback. And we also find a fragmented prompting. That is because we have one person to control the AI, and sometimes he individually controls AI interactions. It has some advantage and disadvantage. For the advantage, it sometimes brings creativity, but sometimes it also brings a breakdown and another kind of the different route of the discussion in our group work. And when people receive the information from the AI, they always have 3 stages. Firstly, they will surfacing the comment, like they need to highlight it, use their hands, or use mouse to highlight them, like what's on our slides. And people then evaluate it, discuss it, and then they discuss to move it into their group work. Our second findings from our observation is people make decisions through navigation with the AI, and we also found 3 different kind of the mode of using it. Firstly is the evaluated adoption, so people use the information from the AI and they discuss it, sometimes they adopt it, and also sometimes they critical reject it. But in our observation, we also find some groups, they organize the AI. So they just say, oh, this is good, and without any further discussion. And our last interesting finding in our observation is the AI interface can also become the cooperative space. So when people want to remember something, they use the AI, the history of it, like a shared memory. So people always search the content they want in the AI, and also people use it as attention orching. So people always focus on the AI and use it as the cooperative space. It's a place for the cooperation, not just the tools for the cooperation. And for our interview findings, we found that it is different from asynchronous using, the daily using, with our observation using. So in their daily use of the generative AI in their teamwork, they always use it like personally. So firstly, they use it individually for their subtask of the cooperation. And then they make a proposal with the AI, discuss with the AI themselves. And at last, they use the content and bring them to the teamwork. Sometimes it's delabeling. People don't know which part is from the person and which part is from the AI. Like our participants says, they usually think about the outcome and don't really care about the process. So now let's move to our discussion. So our discussion is from the human-AI interaction and CSCW to GSCW. So we have the human-AI interaction that is always individual and the AI cooperation together. And we also have the CSCW, which is human and the shared artifacts. So our statement is we want to bring a bridge to these 2 kind of the structure. So generative AI supported cooperative work, and it includes human, generative AI, and the cooperative space. And here are the 5 dimensions we found in our study of the GSCW: the flow, which is the information flow, the awareness, the roles, decisions, and space. In our paper, we have a table to compare with the difference and the similar things in the 3 kind of the structure. And if you are interested in it, you can look our paper to find some interesting things. And here are some design consideration for us. So firstly, we raised the directional context flow. So we think in the future, the system for the cooperation using the generative AI should have support preamble boundaries, so information can move across personal and shared spaces. And it should think about what kind of the information should transfer and what kind of information shouldn't transfer. And then it's role labels, because in the corporation, the role of the generative AI is not like a fixed role. It's changed, and our thinking is make AI's roles in the decision process visible and adjustable. And at last, it is the manipulable artifacts, so we think we should turn AI outputs into adaptable artifacts to support shared memory. And our insights for our research is generative AI must be designed not merely as an assistant, but it can also be an agent and also a shared cooperative space. So this is our research, and if you have any question, I'm happy to answer. And for more details, please read our paper. Thank you.
Thank you very much. Time for questions before the coffee break awaits. I can see a microphone running.
Hi, my name is Dongyab Lee from Sechayk. First, thank you for your wonderful presentation about your works. And my question is, did you consider participants' characteristics such as the trust in AI or AI level of AI literacy? Because this factor may have influenced how actively or critically they use the AI in collaboration environments. So I want to know, considered any for this or observed any related patterns in your works? Thank you.
Thank you for your question, and it is a very good one. So in our this research, we focus on the collaboration nature itself. So we didn't really be careful, or we didn't really pay attention to how people trust of AI and how people like adopt AI or think of the information is correct or not. But it's still a very important question, I think, in the research. Thank you.
Good. Thank you very much. And on that note, I'd like to thank you again for the presentation, Hawaii. And thank you everyone for joining the session, and thank you for the patience and for fighting with the technology in this session. See you around.